right. Here we go, Chemistry 111. So we were just continuing on here with Chapter 9, and we left off somewhere around example 9.2. It says, classify the following bonds as ionic, polar covalent, or covalent. So if we look at the electronegativities of hydrogen and chlorine, and all you'd have to do is step back to that periodic table where I have the Pauling scale of electronegativity. And again, I took that right out of our textbook. You would see that hydrogen has an electronegativity of 2.1 and chlorine has an electronegativity of 3.0. So if I want to figure out the difference in electronegativity, I take 3.0, I subtract 2.1, and I get 0.9. Now, 0.9 is in between 0.4 and 2. And so that means that this is a polar covalent bond. So we'll just call it polar covalent. If we try the same thing with potassium fluoride, KF, you see that potassium has an electronegativity of 0.8. Fluorine, that's easy to remember. It's the king of the castle, right? It's got an electronegativity of 4.0. The difference in our electronegativity, come on, 4.0 subtract 0.8, right? Math you can just do in your head. You get 3.2. Wow, that's a lot bigger than 2. That is an ionic compound, right? And you're like, well, sure, I proved it using electronegativity values, but hey, I knew that potassium fluoride was an ionic compound to begin with because potassium is a metal and fluoride or fluorine is a nonmetal. The next one, I'm not going to go into the entire Lewis structure of this molecule. So this is called ethane, and that's neither here nor there right now. That's something you would learn if you took chemistry 211 or 212. But the bond between the two carbon atoms. Now this one might be a no-brainer, but I'll go over it with you. Carbon has an electronegativity of 2.5. The other carbon has an electronegativity of 2.5. So you know where I'm going with this, don't you? 2.5 subtract itself, 2.5 gives you 0. And so this is a purely covalent bond. This is a non-polar covalent bond. So we'll just call it a covalent bond. And if you want to call it, non-polar, that's fine. If you're the kind of person that likes to look around the internet, you're like, hey, I need more information on this. Sometimes you might see covalent bonds called non-polar covalent bonds or even non-polar bonds. Well, if you remember a few slides ago, I showed you how to draw the carbon dioxide molecule. I spent a little time on that, how to draw the water molecule using Lewis dot symbols. And I promised you that I would show you some quick and dirty rules that you can use to come up with your own Lewis structures. And here they are. So how do you come up with a Lewis structure? Again, it's going to take practice more than anything, but there are some rules that you can use as a tool to help you come up with good Lewis structures. So number one, let's go through these. It says, draw the skeletal structure of the compound, showing what atoms are bonded to each other. Okay, here's a good one. Put the least electronegative element at the center of the compound. Now, that's not going to be true all the time, but a lot of the time in Chemistry 111, that will be true. You know how I tallied up those valence electrons? Like I was doing that with you earlier on. I said, okay, H2O, I got 2 from each hydrogen. I've got 6 from the oxygen. That gives me 8. Well, that's what you're going to do next. Okay, you look at all the atoms. You tally up the total number of electrons. Next, as a sort of a sub point to that, if you will, if you have a negative charge, you're going to add 1 for that negative charge. Let me give you an example. Let's say you were dealing with carbonate, right? You guys know what a carbonate ion is. Well, if I tallied up the total number of valence electrons in carbonate, carbon has 4 valence electrons, oxygen has 6. I have 3 oxygens, so I have 4 plus 6 times 3, but I also have the 2 negative charge. Where do I get a negative charge from? From an electron, and so I have to add 2 onto that, so I would get a total of 24 valence electrons. Right? What if you have a positive charge? Every time you get a positive charge, you'd subtract an electron. Don't believe me? Well, let me show you. Let's say you had an ammonium ion, okay, NH4 plus. Well, how many valence electrons does nitrogen have? It has 5. We've established, I think by now, that hydrogen has 1. We've got 1 times 4. So that would give us 5 plus 4, which would give us 9. But we have a positive charge, so we're going to subtract 1, which gives us 8 electrons overall. Okay? Next rule is one you might have kind of figured out already, which is that we complete an octet, which is, again, atoms like to be surrounded by 8 electrons, except for hydrogen. Now, if you're the kind of person who maybe studied chemistry in high school, or if you read the entire chapter before coming to class, which I hope you did, you might be like, well, come on, there's exceptions to the octet rule, Mr. Dion. Well, in fact, there are very few atoms that actually totally obey the octet rule. But for now, we're just going to hang our hat on that and say we're going to complete an octet for all atoms except for hydrogen, which only needs a duet, right? It only needs the 2 electrons because it only has that 1 s orbital available. Last point, if the structure has too many electrons for it, make double and triple bonds on the central atom as needed. You know, I remember when I was learning this in the first chemistry class that I took, where I learned Lewis structures, and I always think of this point as, I remember the first weekend that I was studying this, and I always think, I would summarize this point as maybe being T&E, right? Trial and error. You got to work at it a little bit. As you become more proficient in it, it's like anything in life. You're going to get more confident. You're going to be able to do it faster. But sometimes it takes a little bit of trial and error. Let's take a look at an example. Let's take a look at an example. And you know what? This example is a great segue into one more rule that I want to teach you. Okay, let's read the problem together. First, it says, write the Lewis structure for nitrogen trifluoride in which all 3 fluorine atoms are bonded to the nitrogen atom. So they kind of gave you a hint here right away. Okay, they're telling you that you've got nitrogen, okay, and you've got all the fluorines bonded to it. I'm just going to put them like this for now. Okay, that's fine. So that's where we would start, maybe. But let's figure out how many total valence electrons we have. We got nitrogen trifluoride. Well, nitrogen has 5 valence electrons. Fluorine has 7 valence electrons. There's 3 of those, so that's 21 plus 5 gives me a total of 26 valence electrons in nitrogen trifluoride. So you ready? I want to show you one more rule, and that is a fluorine, and this is a rule you can hang your hat on, okay? I promise. Whenever you have a fluorine in a Lewis structure, it's only ever going to have 1 bond to it. So anytime you have a fluorine in a Lewis structure, it's always going to look like this. It's going to have a bond, son of a gun, and it's going to have 3 lone pairs, like that. Okay, now that is kind of me cheating a little bit and just kind of giving you the answer away like that. But it is a rule, like I said, that you can kind of obey all the time. So what if we went ahead and we completed the octets of all these fluorine atoms? How many electrons have we used so far? 1, 2, 3, 4, 5, 6. Well, 26 subtract 6 means I got 20 electrons to go. So let's complete the octets of those fluorines. Let's put the 3 lone pairs around each fluorine. So I'll do that. Oops, I'm missing one there. There we go. So now I've used up 8, 16, 24. I've used up 24 electrons. If I look at each one of these fluorines, you can see that this fluorine is surrounded by 1, 2, 3, 4, 5, 6, 7, 8. Every fluorine here is surrounded by 8 electrons. Like I said, I've used up 24 electrons thus far. I've got 2 left over. Can somebody tell me where the last 2 electrons would go? Do I just sweep them under the rug and say, you know, I'm just going to pretend like they didn't happen? Maybe nobody will notice. Thanks, Branson. Yeah, I like your answer. N, right? And you're absolutely right. That's where they're going to go. How was Branson able to figure that out so quickly? Well, he said the nitrogen is only surrounded by 1, 2, 3, 4, 5, 6 electrons. That doesn't have a complete octet. So if I took those last 2 electrons and I put them on the nitrogen like that, then howdy do? Look, 1, 2, 3, 4, 5, 6, 7, 8, hot dog. We have a wiener. Everybody is happy. There we go. We have a beautiful Lewis structure. Give me a thumbs up if you follow me on that. Even if you're like, I'm not sure I could do it right now, Mr. Dion. I'm not sure I could put it together that quickly, but at least I understand the crux of what is going on. Good. Great. I'm happy to see my students are following me, right? Again, don't be intimidated. Don't say, oh, no, you know, I'll never figure it out. You know, I'm the only person. Look, if it was easy, everybody on the street could do it. Right? You could walk up to anybody in the crowd and say, draw me a Lewis structure, you know? Well, it's not easy, okay? And it takes a lot of practice, okay? So I just want to encourage you, don't get discouraged when you're doing Lewis structures. Let's try, in the interest of time, what time is it? 6:25. In the interest of time, let's try another one, okay? I got a good class here. I got a bunch of smart students here that could probably help me figure this one. It says, write the Lewis structure for nitric acid, in which all 3 oxygens are bonded to the central nitrogen and the ionizable hydrogen atom is bonded to one of the oxygens. So we have the formula for our nitric acid. When we did the chemical transformations of copper lab on Tuesday night, if you're in group A, it was reagent we used in the first reaction, right? We took our solid copper, treated it with nitric acid, had to turn on the fume hood. Anyhow, kind of a cool reaction. Anyhow, they've given us some really solid clues here, haven't they? They've told us that all three oxygens are bonded to the central nitrogen, and one of the oxygens has the hydrogen bound to it. So let me show you what they're telling us. We've got a nitrogen. It's got 1, 2, 3 oxygens bound to it, and one of the oxygens has a hydrogen, like that. So that's a clue. Now, am I always going to give you these kinds of juicy clues? I would say no, not all the time. But you know what? When you're starting, there's nothing wrong with having a clue or having a little help to get you started. So let's figure out how many valence electrons we have in nitric acid. Hydrogen has 1, nitrogen has 5, oxygen has 6. There's 3 oxygens. So that means 6 times 4, we've got a total of 24 valence electrons. How many have we used up? 1, 2, 3, 4, 5, 6, 7, 8. We've got our work cut out for us, don't we? All right, we got a lot of work to do. Well, again, I'm going to go over this probably quicker than a beginner would. But let's start by putting some electrons on the oxygens to complete their octet. So again, I used up 1, 2, 3, 4, 5, 6, 7, 8 electrons. 24 subtract 8 means I've got 16 to go. Let's go. If I complete the octet of this oxygen, now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. Everybody's happy. Okay? Everybody's happy. Look, this don't believe me? Look, this oxygen, 1, 2, 3, 4, 5, 6, 7, 8 electrons. Look at this oxygen. 1, 2, 3, 4, 5, 6, 7, 8 electrons. Good. Look at the hydrogen. It's got 1 bond, as always. Can anybody tell me where the problem with my Lewis structure is? And there is a small problem here. Actually, not that small of a problem, but there's definitely a problem here. Can anybody tell me what the issue is with what I've got done here? Why I couldn't give this a 10 out of 10? No? What about the nitrogen? Does the nitrogen have an octet? Hey, is the nitrogen surrounded by an octet? Look, I've got. Yes, there we go. Thanks. Excellent. Good. The nitrogen has 1, 2, 3, 4, 5, 6. It's not surrounded by an octet, is it? No, it's not. Well, what if I took one of the pairs of electrons from one of these oxygens, okay, and then I made a bond like this. Now, and I could have done it with this one as well, but now you see that my nitrogen is surrounded by 1, 2, 3, 4, 5, 6, 7, 8. And both of the oxygens, or sorry, all 3 of the oxygens have a complete octet. Here we go. All right. Now, again, if you've spent some time reading our textbook, you probably know that this Lewis structure isn't 100% complete, is it? If you haven't read the textbook, you might be like, what's wrong with that? There's nothing wrong with it. This is beautiful. Well, there's something missing from this Lewis structure, but I want to move on before we get into what is missing from this Lewis structure, and we'll talk about it later on, okay? Let's try one more example. It asks us to come up with a Lewis structure for the carbonate ion. And whenever you read any kind of introductory chemistry textbook, there's always a question about the carbonate ion. Carbonate ion is CO3 2 minus, right? It's one of the polyatomic ions that we learned earlier on. We already tallied up the valence electrons, didn't we, a couple of slides ago? So we've got 4 plus 6 times 3 plus 2. We've got a total of 24 electrons. Now, it doesn't tell us how the carbon in the 3 oxygens are connected. However, if we go back to our rules, we said we're going to put the less electronegative element in the center. So let's do that. Let's start with that rule since they haven't given us any tips. So we're going to do this. We're going to say carbon, we got 1, 2, 3 oxygens surrounding it like this. So now we've used up a total of 6 electrons. So that means I've got 24 minus 6. I got 18 to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There we go. Hot dog, we have a wiener. So we've got 18, 19, 20, 21, 22, 23, 24. Everything is used up. There we go. I see that each oxygen is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. Good. No, it's not, is it? Because my carbon is only surrounded by 6 electrons. And so I'm going to have to take one of the lone pairs. Now, if you're wondering, and this would be really splitting hairs, but if I have a student out there, you know, in Microsoft Teams land who's like, well, which one of these, can I take that one? Can I take this one? Can I take, the answer is you could take any one of the lone pairs on any one of these 3 oxygens. I'll just pick one at random. I'll erase those 2. Maybe I'll make it prettier than that. Okay. And I'll make a double bond like this. Now each oxygen has an octet and the carbon has an octet. Okay, so I have to adjust my bonds. I have to make double bonds if they're necessary in order for every element to have a complete octet. Now, there's an elephant in the room here, right? The 2 minus charge. Now, again, I'm going to introduce the concept of formal charge in just a second. But before we do, if any of you have taken an introductory chemistry class that might be a lower level chemistry class than this, and I think a couple people have done that, what you may have learned, or maybe some people might have learned in high school, is that you would just take the Lewis structure and you would put some square brackets around it like this, and you'd say, well, it's an ion. Everything in here is good. All my octets are filled, but it's got a 2 minus charge like that. Now, that is not where we're going to stop in Chemistry 111. Okay, this is General Chemistry 1. I'm going to teach you how to assign what are called formal charges. Okay, and again, in the interest of time, I'm going to skip this this slide. No, I'm not going to skip this slide. What I'm going to do is I'm going to skip the whole thing. I'm going to skip example 9.7. So if you read chapter 9, and when I say if, I mean you should be reading chapter 9. You paid for the book, okay? So example 9.7 is basically this kind of treatment where it talks about coming up with a Lewis structure for formaldehyde, right? If any of you have taken biology, you know what formaldehyde is. It uses a preservative, okay? Anyhow, it goes through a whole treatment of formaldehyde and how there's 2 possible ways that you could put formaldehyde together in order to get an acceptable Lewis structure where all the atoms have complete octets. And again, I'm not going to go through this in gross and gory detail, but the whole point is this, is that if you draw one of the Lewis structures, and this is not the correct Lewis structure for formaldehyde, you end up with what are called formal charges. Now, if you're like, what's a formal charge? A formal charge means that you have a charge which is either +1, -1, could be a +2 or -2, but we try to avoid those. It means that you've got an actual charge on an atom. So you can see that in this Lewis structure, and I'm going to go over how to calculate formal charge in a second, but you've got a formal charge on the carbon and the oxygen. So you're like, well, can I do better? And the answer is yes. And again, I'm kind of going over this quickly just in the interest of time. If you look at this Lewis structure here, you see that there are no formal charges. Now, let me back up and tell you how to calculate formal charge. So formal charge is the difference, and I'm just reading the definition here. Formal charge is the difference between the number of valence electrons of the isolated atom, so the number of valence electrons of the Lewis dot symbol, right, and the Lewis dot symbol in that periodic table of the isolated atom, and the number of electrons assigned to that atom in the Lewis structure. Now, I have a treatment here, which I think I took directly from the textbook. Okay, I'll just read it to you once, and then I probably won't say it again because I have an easier way. There, remove my margin. You say the formal charge is going to be equal to the total number of valence electrons. You subtract the number of non-bonding electrons, so those are the little dots that aren't in a bond. Subtract half the number of bonding electrons. What's a bonding electron? That's an electron that's in a bond. So, are you ready for Mr. Dion's treatment that is easier for students to remember? Formal charge is going to be equal to the number of valence electrons, subtract the number of dots, subtract the number of sticks. Okay, a stick is a bond and a dot is a dot. Watch. Let's go back to this carbonate and let's assign the formal charges in carbonate. Let me show you how. If I look at my carbon, carbon has 4 valence electrons, subtract the number of sticks. How many sticks are there around carbon? 1, 2, 3, 4 sticks. Okay, so subtract 4 sticks. How many dots are there on the carbon? There are no dots. 4 minus 4 minus 0 gives you 0. There is no formal charge on the carbon. Let's try this oxygen up here. Oxygen has 6 valence electrons. How many sticks? 1, 2 sticks. 6 subtract 2. How many dots? 1, 2, 3, 4 dots. 6 subtract 2 subtract 4 gives you 0. Hot darn it, still don't have a formal charge, okay? Well, let's try the other oxygens, okay? Let's keep moving. This oxygen has 6 valence electrons. Subtract 6 dots in 1 stick. Aha, -1. Same thing here. 6 minus 6 dots minus 1 stick gives you -1. So that means we have a -1 charge here. We draw a negative just like we would for an anion, minus charge in a circle, and we have a negative over here. And that would be the correct Lewis structure, okay? Would be to write your carbonate ion like this. I'm just going to do it quickly for you, okay? You put a negative charge here, a negative charge here. You have -1 and a -1. -1 plus -1 gives you -2, right? Right, the old 1 minus 2 is negative fun, right? Anyhow, there you go. Give me a thumbs up if you follow me on formal charge, because we're going to calculate it a whole heck of a bunch of times moving forward. Thanks, Branson. I really appreciate it, man. I really appreciate it. Well, let's go back to example 9.4. Can we assign a formal charge here? Yeah. Does anybody recognize, or can anybody figure out quickly where there would be a formal charge in the nitric acid molecule? Where I might find one on what atom? And you can make the answer as simple as you want. Based off of what you just saw in the carbonate, you might recognize a pattern here. No? Okay. Well, if you don't recognize a pattern, yeah. Okay, thanks, Branson. It's on the oxygen, right? And there's some quick and dirty rules that we could learn about this, but in the interest of time, you can see that this oxygen has a negative charge, and the nitrogen actually has a positive charge, right? The oxygen has a negative charge because it's 6 minus 6 dots in 1 stick. That gives you -1. The nitrogen is 5 valence electrons. Subtract 4 sticks and 0 dots. That gives you +1. Well, that's good because nitric acid is a neutral molecule, isn't it? And if we have a +1 and a -1, what happens when you add +1 and -1? You get 0. They cancel out. There you go. So what have we covered since the break? We've covered Lewis structures, the rules for Lewis structures. You're going to have to practice those Lewis structures. There's no shortcut that I can give you to just, there's the magic pill, and now you know every Lewis structure under the sun. No, they just take practice, and now you know how to assign formal charge. Okay, Lewis structures and formal charge. Well, I've gone over formal charge with you. I've gone over, I talked about formaldehyde. What I'd like to do with you then is take a little bit of time. What time is it? 6:38. We've got 6 more hours. So I would like to try some other Lewis structures with you just for fun. Now let me back up here. I thought I'd put a blank page in here somewhere. No, I didn't. Here we go. Yeah. Well, let me see here. I'd written down a couple that I thought would be good ones to try. I'm going to write down 2 on the screen. And if you think I'm going too slow, feel free to move on from there and, try something else. But I would like you to try these 2. So CS2, which is carbon disulfide. So you could give that one the old college try. And another one that you could try is, what else did I have? PCl3, so phosphorus trichloride. I think that you're all old enough to try these ones. So I'm going to give you a second, about a minute, to just take a look and see if you can tally up the number of valence electrons and even get started. I get a drink of water. Could anybody tell me how many total valence electrons there are in CS2, carbon disulfide? And it's not a trick question. Mr. Dion hates trick questions. So I'm not sure. I'm getting some interesting answers here. Well, how many valence electrons? Okay, let me back it up. Okay. How many valence electrons does carbon have? Who could answer that? Good. Okay, you're all 100% correct. Nothing wrong there. How many valence electrons does one sulfur atom have? Sulfur is right below oxygen in the periodic. Perfect. So if I have 6 times 2, right, because there's 2 sulfurs, so that means I have 12 valence electrons here, and I have 4 valence electrons here. So 4 plus 12, that gives me a total of 16. Does that help? Does that make more sense? Yeah, that I have a total of 16 valence electrons. Okay. All right. Hopefully that helps a little bit. Now, how would we assemble this together? Well, I mean, you got a carbon and 2 sulfurs. Remember, we said that we put the less electronegative element in the center. Now, there isn't a big difference in electronegativity between carbon and sulfur. Carbon is around 2.5 and sulfur is around 2.6. Not a big difference, but what we'll do is we'll put our carbon in the center and we'll attach the 2 sulfurs to it like that. Now, if you're wondering, hey, Mr. Dion, why won't you do something like this? Just put them, close together like that. Well, the reason is that for now, when I draw my bonds, I try to put them as far away from each other as possible. Why? Because electrons are negative, right? We know that there are electrons in this bond. We know that there are electrons in that bond, and electrons repel each other, don't they, right? Like charges repel. Opposites attract, but like charges repel, and that's why I'm drawing it that way. Okay. Now we've got that far. So now we've used up a total of 4 valence electrons. We've got 12 more to go. Where are we going to put them? Well, what if I filled up the octets of the 2 sulfurs? Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now both of my sulfurs are surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. There's a big problem here, though, isn't there? My carbon is only surrounded by 4 electrons. It needs to have an octet. What am I going to do? I'm going to start erasing electrons. I'm going to remove that pair of electrons. I'm going to make a double bond. Both sulfurs in this molecule, the way it's drawn right now, both sulfurs have a complete octet. But my carbon still doesn't have a complete octet. And so what I'm going to do is I'm going to do the same thing with the other sulfur. I'm going to erase a lone pair, and I'm going to make a new bond here. Now, if we look at the structure, you see that the sulfur has 1, 2, 3, 4, 5, 6, 7, 8 electrons. The carbon is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. The formal charge on the sulfur is 6. Subtract 2 sticks, 4 dots is 0. The formal charge on the carbon is 4. Subtract 4 sticks and 0 dots is 0. There we go. So that means we've got a perfectly great Lewis structure here. All the atoms have complete octets. There's no formal charges. Everything is good. So that would be a perfectly good Lewis structure for carbon disulfide. I'm going to do PCl3 a little bit quicker. Okay, a little quicker, and I'm going to show you one more trick before we move on, because I'd like to talk a little bit about resonance structures with you before we move on, but that's not that important right now because we've covered quite a bit of content. I want to spend maybe a little more time on Lewis structures. Well, what about my PCl3 molecule? Can anybody tell me how many valence electrons there are in PCl3, phosphorus trichloride? And again, it's not a trick. Mr. Dion doth hate tricks. Thanks, Kristen. Awesome. Okay, so Kristen Benke says there's 26. All right, both Kristen say there's 26. Well, there's power in numbers. Let's see. Anyhow, phosphorus has a total of 5 valence electrons, right? Phosphorus is just below nitrogen. It's in group 5A. Chlorine is a halogen, right? By now you have the halogens memorized. Fluorine, chlorine, bromine, iodine. They all have 7 valence electrons. So 7 times 3 is 21. 21 plus 5, we've got a total of 26 electrons. I like the way my students think. So now what we're going to do is we're going to put the phosphorus in the middle, and we're going to draw 3 bonds to chlorine. Now I'm going to space them evenly like this. Okay, the phosphorus is surrounded by 6 electrons, but you remember that earlier on I told you, and I'll just put it in a box down here, I told you that fluorine only ever has 1 bond and 3 lone pairs. Well, it's not necessarily true for all of the other halogens, but I'll just tell you, it's a safe bet a lot of the time, okay? Not all the time, but a lot of the time, chlorine is going to have one bond, 3 lone pairs. Bromine will have 1 bond, 3 lone, son of a gun, need a new prescription, 3 lone pairs. And then iodine, a lot of the time, will have 1 bond, 3 lone pairs. Next lecture, we're going to cover what's called an expanded octet. Don't worry, Mr. Dion knows all about expanded octets. If you've read ahead and you're like, Mr. Dion, you're forgetting, I know about expanded octets. We're going to cover that next class. But for now, a lot of the time, not all the time, but a lot of the time, the other halogens will only have 1 bond and 3 lone pairs. So let's try that first. It's a good place to start. We've got 26 electrons. We've used up 6 electrons. So that means we've got 20 left to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, each one of the chlorines has a complete octet, right? Look at it. Every chlorine is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. Looks pretty good, doesn't it? Branson or anybody, where are my last 2 electrons going to go? Because I've only used up 18 more. I've got 2 electrons left. Where are they going to go? Thanks. Perfect. They're going to go on the phosphorus, aren't they? Absolutely, that's where they're going to go on our central atom. I'm going to erase some of this spinach that's in the way here. Okay, there we go. Let's double check the formal charge in our phosphorus. Phosphorus is in group 5A. 5 valence electrons, subtract 3 sticks, 2 dots, 0. Each chlorine is identical. 7 valence electrons, subtract 6 dots, 1 stick, 0. No formal charges on any element there. And there we go. I've got a beautiful, beautiful Lewis structure, and there's nothing wrong with that Lewis structure at all. There we go. So what would be a good strategy for you between now and our next lecture? What I would like you to do between now and then is study chemistry 8 hours a day. No, I'm a realist, but I would like you to look at the practice problems that I hand selected from our textbook, and I would like you to try as many of the problems as you can from chapter 9. Really tackle those Lewis structures. Again, and I know I'm repeating myself, but you know what? I'm 44, I'm middle-aged. I've earned the right to repeat myself like an old man. And so I want you to make sure you spend enough time